Hi, my name is Paolo Ferro and I work at the University of Padova. The topic of this talk is about a method to manage critical raw materials in mechanical design. This method was developed in the context of an European project called Design of Component in a Critical Raw Material Perspective, of which I am the coordinator. These are the contents of my presentation. In particular, I will focus on material selection and methodology in a critical raw material perspective, and I will illustrate the method with an example. What are critical raw materials? Critical raw materials are those raw materials that are, number one, economically and strategically important for the European community, and number two, they suffer from a high supply risk. Think, for example, to those materials linked to green economy, electric vehicles and battery. But we can find them also as alloy elements in mechanical components. Therefore, some alloys are more critical than the others. Mitigating actions are required to reduce the issues linked to critical raw materials, such as substitutions, increased material efficiency, and recycling. Here you can see highlighted in green critical raw materials resulting from the report of the European Commission. Note that the main indicators are the supply risk and the economic importance, but they are not the only ones. The goal of this work is to find a strategy for material selection in mechanical design with the aim to reduce the drawbacks linked to critical raw materials. The proposed methodology is based on the alloy criticality index definition and follows the method first developed by Ashby. One of the main challenges in raw material criticality assessment is how to aggregate the above-defined indexes in only one material criticality index. For the sake of simplicity, the overall criticality index of a critical raw material I is obtained by averaging 6 criticalities indexes values as shown in this slide. They are the abundance risk, the sourcing and geopolitical risk, the supply risk, the economic importance, the end of life recycle input rate, and environmental country risk as well. Their formula and values are defined by the European Commission, and the list is updated every 3 years. By moving from the single raw material to the alloys containing different critical raw materials, the alloy criticality index can be quantified by the following equation, where N is the number of critical raw materials in the alloy chemical composition and Vt% is the amount of the generic critical raw material I in the alloy, measured in weight percent. It is observed that the alloy criticality index represents an overall criticality values per unit of mass of the alloy. Now, the material selection strategy is based on the famous Ashby approach that consists of 4 steps. Number 1, definition of the design requirement in terms of constraint, objectives, and free variables. Number 2, screening using constraints. Number 3, ranking using objective. And number 4, seeking supporting information. As case study, I'm gonna show you the procedure for material selection in a pressure vessel new design. When it has to be mobile, its weight becomes important. Aircraft bodies, rocket casing, and liquid natural gas containers are examples. They must be light, and at the same time they must be safe. Therefore, they must not fail by fast fracture. The three variables are the material and the thickness. It is assumed that the component is, for simplicity, spherical of specific radius r, and that the wall thickness T, the three variables, is small compared with r. Then the performance equation for the mass m of the pressure vessel is given by the following formula, where ρ is the material density. By equating the tensile stress in the wall of the pressure vessel with one that promotes an unstable crack propagation, it is possible to obtain the value of the free variable T. Now, by substituting the just obtained free variable expression into the objective equation, the mass, and by isolating the material's properties only, the material index M is obtained. Now, critical raw materials may be contained in different amounts in the alloy composition. Therefore, an alloy criticality index can be defined as described before. So, in a critical raw material perspective, the objective to be minimized will be the criticality of the design component. This objective is formulated by multiplying the mass of the component M by the alloy criticality index. Following the same above described procedure, the new performance equation and index M star can be easily obtained as shown in this slide. Pressure vessels are commonly made by low alloy steels. For substitution purpose, it is therefore more convenient to plot the relative values of the material indexes as shown in the figures, where M0 and M0 star are the material indexes values of the actual pressure vessel steel. The point of coordinates 1, 1 in this figure is occupied by the steel to be substituted. The two straight lines across that point divide the plot in 4 quadrants named A, B, C, and D. The solutions stay in the quadrant A, where alloys that allow producing both less heavy and less critical pressure vessels are found. In this example, if the criticality issues are evaluated much more seriousness than weight reduction, the solution moves to the titanium grade 1 or the aluminium AA 1080. On the other hand, if the criticality issues and weight reduction are evaluated equally, the nickel-based alloy should be considered as a good substitute in a critical raw material perspective. Finally, verification and supporting information need now. Think about limits in the free variables, for example, but anyway, the method allows reaching systematically other possible solutions. This is me, and these are my contacts. Thanks for your attention.